Hello friends. So in today's lecture we are going to study frequency division multiplexing, time division multiplexing and code division multiplexing. When these multiplexings are used to access the channel, then it becomes frequency division multiple access. This becomes time division multiple access, and this becomes code division multiple access. Now let us study one by one. So first of all, we are going to study frequency division multiplexing. Now, what is frequency division multiplexing? In this, multiple signals are combined into a single composite signal for transmission over a channel. Now, same channel is used for the transmission of multiple signal. So basically we are increasing the capacity of the channel, or we can say that channel is now more efficiently used. Now in this we will do the multiplexing in frequency domain. That is why it is called as frequency division multiple access or frequency division multiplexing. In frequency division multiplexing, each user, or I can say each message signal, is given a unique frequency spectrum to transmit itself. And frequency division multiplexing is generally done for analog modulated signals. So these are the few basic things about the frequency division multiplexing. Now let us have a look. How does it look like? Suppose the user 1 or the message 1 is M1T and it has spectrum like this. This is from -5 kilohertz to +5 kilohertz, and this was our baseband spectrum. And user 2 or message signal 2 has spectrum -5K to 5K. This is M2F versus F. And third message signal has the spectrum like this. Now we want to transmit these signals by using frequency division multiplexing. So what we will do, first of all, the message signal will be band limited by passing it through a low pass filter. Second message signal will also be band limited by passing it through the low pass filter. And third message signal will also be band limited by passing it through a low pass filter. Now we will modulate it by using a modulator. This modulator may be amplitude modulator or double sideband suppressed carrier modulator or SSPSC modulator. Practically SSPSC modulator is used. These two in general is not used, but for theory we will consider all these three modulations. So this was our modulator 1. I am assuming here a carrier C1T, and it will generate the modulated signal S1T. Now this second signal is also modulated. I'm assuming here carrier again C2T, and this will generate a modulated signal S2T. Now I'm considering third modulator, which has a carrier frequency C3T, and the signal which is modulated comes out to be S3T. Now these three signals are combined and it is transmitted over a wireless channel. Now we know that the first block of a receiver is a tuned amplifier, which is nothing but a band pass filter. So at the receiver side we will have band pass filter. This will be also a band pass filter, and here we will be getting band pass filter. Now since we have combined this signal here, so at the receiver side we'll be getting the combined signal S2T plus S3T. The band pass filter will filter one signal. Here also it will filter the second signal, and it will filter the third signal. Now once the modulated signal is obtained, now here we can use a synchronous detector, and carrier frequency will be C12 followed by a low pass filter, and it will generate the message 1. Here also once we get the modulated signal, we can use the same carrier, and it will be followed by a low pass filter, and at the output I will be getting M2T. Now for third modulated signal I am again using the carrier. It will be followed by a low pass filter, and I will be getting third message. So this is our transmitter and this is our receiver, and this block is acting as a synchronous detector, and this is nothing but tuned amplifier. Now let us study two cases. In case 1 is we are considering the carrier frequencies of the carrier at the transmitter to be same, and that is FC. Now our message signal M1T has the frequency spectrum like this, from minus 5 kHz to plus 5 kHz. Now again, once it is passed through the modulator and it is modulated by a carrier of frequency FC1, so the modulated signal S1T will have spectrum something like this. It will shift the message signal spectrum over its carrier, so it will be FC1, but FC1 is nothing but FC. So this is the spectrum of S1F. It will be FC plus 5K, it will be FC minus 5K. This frequency will be FC plus minus FC plus 5K, and this will be minus FC minus 5K. Now the message signal M2T was also having the frequency from minus 5K to 5K will be F. This frequency will be M2F. Now it is passed to the modulator. It is modulated by the carrier of frequency FC2, and it is nothing but FC. So we will get the modulated signal S2T, and the modulated signal will again have shifted version of message signal, and this shifting will be on the carrier. So it will be FC plus 5K, it will be FC minus 5K, this will be minus FC plus 5K, and this will be minus FC minus 5K. Similar discussion can also be done for third message signal. So the shape was somewhat rectangular, so I'm drawing it like this. So this is M3F, this is also passed through the modulator, and it is also modulated by a carrier. FC3 is equal to FC. We are getting third modulated signal S3T, and the spectrum is coming out like this from FC to FC plus 5K, FC minus 5K, minus FC plus 5K, minus FC minus 5K, and this is our S3F versus F, and this is S2F versus F. Now once these three signals are added, S1T plus S2T plus S3T, their spectrum also gets added. And since both the three spectrums are occupying the same frequency spectrum, so we get some distorted signal between FC minus 5K to FC plus 5K, and similar distorted signal at the negative side also. And this is the combination of S1F plus S2F plus S3F. Now at the receiver we will be having a band pass filter. This band pass filter will have center frequency as FC and cutoff frequencies at FC plus 5K and FC minus 5K. So the output spectrum will be a distorted signal FC minus 5K, FC plus 5K versus F. This is the distorted signal S1F, and similarly when it is passed through the second band pass filter and third band pass filter, at the output of all the three band pass filters we are getting a distorted signal. So the distorted signal is looking like this. This is our S1F, this is our S2F, and this is our S3F. Because we chose the same carrier frequency to shift the spectrum of each message signal, that is why their spectrum gets added, and they in turn produces a distorted signal which is not our original signal which was modulated. This is also not original, and this is also not original signal. So from this discussion we concluded that if we want to do frequency division multiplexing, so at least we should choose different carrier frequencies for different users or different message signals. Now let us have a case 2. In case 2, this was our message signal M1T, and it has spectrum like this, minus 5K to 5K. Now once it is modulated, this time I am assuming that carrier frequency FC1 is different from FC2 and FC3, so we will get the modulated signal, and the modulated signal will have spectrum which is shifted version of message signal, and this shifting will be done at the frequency of FC1. So this will be FC1 plus 5K, this will be FC1 minus 5K. Similarly for M2T, which was having spectrum between minus 5K to 5K, when it is passed through the modulator, which is having a different frequency S2T. So the S2T's spectrum will have a different shifting component, that is FC2. This is the spectrum of S2F. Similarly, for M3T, we can also choose a different carrier frequency from minus 5K to 5K when it is passed through the modulator, which is having a different carrier frequency as FC3. So the output will be S3T, and the output is shifted version of input signal, and this is shifted at different frequency FC3. So once these S1T plus S2T plus S3T is combined, so their spectrum will look like this. One part is centered at FC1, second part is centered at FC2, and third part is centered at FC3, and obviously they are negative counterparts also. So this is basically rectangular. So this is minus FC1, this is minus FC2, this is minus FC3. So this is our combined signal. Now at the receiver side we have 3 band pass filters. So one band pass filter is centered at FC1, second band pass filter is centered at FC2, and third band pass filter is centered at FC3. So these three are the band pass filters, which is tuned filters. Now what will be the output of these filters? So the output of first band pass filter will be the signal S1T. The output of the second band pass filter will be signal S2T, and the output of the third band pass filter will be S3T. Now by passing it through a synchronous detector, we can recover the original message signal, which was M1T in this case, which was M2T in this case, and M3T in this case. So here we came to know that for frequency division multiplexing, if a signal M1T has spectrum like this, which is from minus B1 to B1F, so the bandwidth of this message signal will be B1. Now once it is translated to a carrier frequency FC1, so it becomes FC1, FC1 plus B, FC1 minus B, and this will be S1F versus F. So the bandwidth of this S1F becomes twice of B. Similarly, for the signal M2T, which is band limited to, I am assuming a different band, so it will be B2, so the bandwidth will be B2, and when it is translated to FC2, so the spectrum becomes FC2 minus FC2, so it becomes FC2 plus B2 and FC2 minus B2, so the bandwidth becomes twice of B2. Similarly for M3T, this is M3F, I am assuming that it is band limited to B3, frequency F, so once it is modulated FC3, So it becomes FC3 plus B3 and FC3 minus B3, and its bandwidth becomes twice of B3. So here we can see that for the discussion we considered a double sideband suppressed carrier modulation. That is why the bandwidth B is translated to twice of B1, or B2 is translated to twice of B2. If I have assumed here single sideband suppressed carriers, then the bandwidth of the modulated signal would have B1, B2 and B3. Now let me draw the multiplexed signal. So the multiplexed signal S of F will look like this. We'll have translated version at different frequencies, this and this one, and obviously they are negative counterparts. So this is FC1 and this bandwidth is twice of B1. This is FC2 and this bandwidth is twice of B2, and this is FC3 and this bandwidth of twice of B3. So what is the total bandwidth of multiplexed signal? The total bandwidth comes out to be twice of B1 plus twice of B2 plus twice of B3. Now we can also see that there is a guard band between these two signals. Let me call this as G1 and G2. So I should also add these guard bands as well. So the total bandwidth comes out to be the bandwidth of S1T plus bandwidth of S2T plus bandwidth of S3T plus guard band between 1 and 2 and guard band between 2 and 3. So if we want to calculate the bandwidth of a frequency division multiplexed signal, we simply need to calculate the bandwidth of first modulated signal, and if the modulation is AM or DSB, it will be twice the maximum frequency component, and if it is SSB, then it will be only maximum frequency component. Bandwidth of S2T plus bandwidth of S3T plus guard band between 1 and 2 and guard band between 2 and 3. So this is the formula of the bandwidth of a frequency division multiplexed signal, and obviously the channel bandwidth should be more than the bandwidth of the frequency division multiplexed signal. So this is all about the frequency division multiplexing. Now let us understand what is time division multiplexing. In case of time division multiplexing, the signal is multiplexed in time domain. So the signal is occupying entire bandwidth but at a different or unique time slot. So here the bandwidth is divided in terms of time. Now let us have a general look about the time division multiplexing. So time division multiplexing actually looks like we have a signal M1T, and let me draw this signal as something like this, and a signal M2T which is looking like this, and a third signal M3T which is looking like this. So these three are our analog signals. So if we want to transmit M1T digitally, then first of all I have to sample it, then I will quantize it, and then I will encode it. So instead of sending only a single signal, I am interested in sending these three signals simultaneously, or I am interested in the multiplexing of these signals. So instead of using the sampler block, I'll be using another block which is similar to sampler, and it is called as commutator. So commutator is doing nothing but it is actually doing the sampling of all these three signals simultaneously. So it will be getting M12, M2T and M3T, and the output of the commutator will be a quantizer followed by an encoder, and after encoding, in order to transmit it through the wired channel, I will line code it, and it will be transmitted through a wired channel. Now let us have a look what will happen. Once this commutator starts moving, let us say at the time of the T1, it is taking the sample of M1T, and at time T2 it will take the sample of M2T, and at time T3 it will take the sample of M3T. It will start moving, and once the M1T comes in the periphery of this, it will suddenly take the sample of M1T. So how will the output of the commutator look like? I am assuming that one rotation or one revolution of commutator is equal to sampling interval. So the output of the commutator will have three samples. This is sample of M1T, this is sample of M2T, and this is the sample of M3T, and this is time slot T1, this is time slot T2, this is time slot T3, and the duration of this is Ts. This is known as a TDMA frame. One TDMA frame consists at least one sample of each of the signal, which is M12, M2T and M3T. Now this frame is encoded. So this was our frame T1, T2, T3, and this was the sample of M1T, this was the sample of M2T, and this was the sample of M3T. So what will be the output of quantizer? So quantizer will basically quantize these values. So it will map it to the nearest integer. So it will be this M1T, M2T and M3T, and the time slot will be T1, T2, T3, and the complete duration will be equal to the frame size, which is sampling interval. Now what will be the output of encoder? Encoder will encode all these quantized sample into some bits. I'm assuming that for one sample it is encoding it by using 3 bits, or I can say that for encoding it is taking 3 bits per sample. So it will be 001, 010 or 011. So it has encoded it. Now it will line code it, and it will transmit this signal. So from here now I can write what exactly is the value of Ts. So what is Ts? Ts is the sampling interval. So the sampling interval will always be equal to the duration of this frame, and if one bit is taking the duration of TB, so let me count here, 1 2 3 4 5 6, there are 9 bits, so it will be equal to the duration of 9 bits. So the sampling interval can be written as Ts is equal to 9 TB. Now let me break this. Here we are multiplexing 3 signals, so I can write it as 3 multiplied by, I am using 3 bits per sample, so I can write again 3 and becomes TB. So I can generalize the formula of TS if there are n signals which are time division multiplexed and they are band limited to same frequency. This is very important. We can write this only when all the n signals are band limited to same frequency. In that case, the frame size becomes n into small n into TB. And what is small n here? Small n is the number of bits per sample. How many bits we are using to represent one quantized sample. So we can write some formulas here. So the first formula is, we know that in TS seconds there is one rotation of commutator, or I can write in 1 second there is 1 by TS rotation of the commutator. So the speed of the commutator can be written as one by TS rotation per second, or I can also write the speed of commutator as is Fs rotation per second, or Fs into 60 rotations per minute. This formula is important. I have already calculated the frame size. This is n into TB. So I can also calculate the sampling rate from here. So the sampling rate comes out to be bit rate divided by small n into n, or the bit rate can be written as capital N into small n into Fs. The bandwidth is Rb by 2. Now let me consider the second case, in which I am considering that the signals M1t, M2t, or the nth signal also are band limited to different frequencies. So in this case, the M1t is band limited to FM1, so its sampling rate will come out as twice FM1. Similarly, the second message signal is band limited to FM2, so the sampling rate will become twice of FM2. The third signal is band limited to FM3, so the sampling rate comes out to be FM3, and so on. Now in this case, if I want to find out the frame size, so the frame size becomes Ts is equal to maximum of Ts1, Ts2, Ts3, and we know that Ts1 is equal to 1 by Fs1. Now the speed of the commutator will be equal to the HCF of Fs1, Fs2 and Fs3 into 60 RPM. The bit rate in this case will become n into Fs1 plus Fs2 plus Fs3, and the bandwidth becomes Rb by 2. Now let us have a look on a CDMA. What is a code division multiple access? So in case of code division multiple access, each user is differentiated in the channel by a unique code. and this unique code is known as pseudo-random, or sometimes it is also called as pseudo noise, which is in short PN code. So what happens in this case is that the information of a user is transmitted in the form of bits, and further it is line coded. So I'm considering that the information is this which we have to transmit. Now this information is first of all coded by using the pseudo noise code at the transmitter. After coding, it is passed through the any band pass digital modulating scheme such as ASK, PSK, FSK. Now it is wirelessly transmitted. At the receiver, we have a band pass receiver scheme, and the same pseudo random code is multiplied here. Then we again get the original message signal which was transmitted. So this is very simple technique. Now let us have a look what is a pseudo random code. So this was our message signal which we want to transmit. Now the duration of this signal was TB, or let me call that the bit rate is RB. So this duration is TB, and the bit rate or the information rate for the user information is RB. Now the pseudo code which is being mixed with this signal will look like this, and the duration of this will be TC. So from here we can see that this code has the bit interval of TC which is very much less than the bit interval of TB, or I can also say that the code rate is greater than the bit rate. This code rate is also called as chip rate, and this pseudo noise code sometimes is also called as chip. Now in order to mix the user information and code, let me multiply this. So I'll be getting the coded signal. So upon multiplication we get like this. So this is our coded message signal. Now let us have a look. We are transmitting bit by bit information. So this was user's information and this was the coded information after mixing with the chip or code. So what we are doing here is we are basically doing bit by bit transmission. So first of all, if I would not have been coded this information, then I would have transmitted this bit first, and it will have spectrum something like this, 1 by TB minus 1 by TB. Now instead of transmitting this bit of TB, I am transmitting the coded information which is having the duration of TC, and TC is very much less than TB. Now if it is compressed in the time domain, obviously it will have a wide spectrum, or this is also known as spread spectrum. So because of mixing the user information with the code, I have actually spreaded the spectrum. That is why CDMA sometimes is also known as spread spectrum technique. Now here we must know some important point. First is, in CDMA there is a spread spectrum, which we understood why it is called as spread spectrum. Second point is, each user or each message signal is assigned a unique code at the transmitter, and this unique code is also assigned at the receiver. So if I want to say that I have 8 different codes, then how many users I can accommodate? So obviously if I am giving different codes to different users, so I can accommodate 8 users only. That is why we generally use 64-bit codes, which generally generates 2 power 64 different codes, and we can accommodate 2 power 64 users. Third point, we noted that the chip rate was very much greater than bit rate, and if I take the ratio of RC by RB, so it comes out to be greater than 1. If any ratio is greater than 1, so we generally call it as gain. So the processing gain of a code division multiple axis comes out to be chip rate divided by bit rate. So that's all from it, guys. Thank you.